So the topic of today's lecture is constructing a compact scheme for one-dimensional transfer equation. We will start with the theory. The following differential equation in partial derivatives is called the transfer equation. Here, u is a function of space x and time t. Since we have only one spatial variable x, this equation is called one-dimensional. And lambda here is a constant parameter, which has the physical meaning of velocity. So basically, this equation models transfer of some substance along the x line, for example, a tube. Since the right-hand side of the equation is 0, this equation is called homogeneous. Otherwise, if we have a right-hand side function of x and t, it would be an inhomogeneous equation. But here we concentrate on the simple case. We can construct a general solution of equation 1, which is of the following form: an arbitrary differentiable function f from one argument x minus lambda t. It can be verified by just substituting this formula into the equation 1, that for any continuously differentiable function f, this resulting function will satisfy this equation. In order to have a unique solution, which is typically what we expect from physical problems and different applications, we need to set appropriate initial conditions, meaning the value of the unknown function at the start time, and boundary conditions, because in numerical calculations, usually we have a limited bounded region. Therefore, boundary conditions are required. Here we will assume that the velocity lambda is positive, meaning that the initial impulse will propagate to the right. And we can consider the Cauchy problem for the transfer equation 1. So we have the original differential formulation of the problem. Time changes from 0 to some t, and x here is in the line segment from 0 to 10, but obviously we can choose arbitrary bounds of the region. Then we have the initial condition. Here it's some function u with the subscript 0, and we can set an arbitrary function like this, and each function u0 will result in a unique solution of the equation. Also, we need to set appropriate boundary conditions. Since lambda is positive, it means that the impulse propagates from left to right. Therefore, on the right boundary, we will have the values coming from the left, from inside the region, and on the left boundary, we have to set an appropriate boundary condition. Here we set a boundary condition of Dirichlet type, just setting the unknown function at the left border of our computational region to 0. So this Cauchy problem has a unique solution. We are going to find this solution numerically using the grid characteristic method. This method is based on the characteristic property of the transfer equation, meaning that any line, a straight line given by this equation, where c is an arbitrary constant, has such property that the solution value is constant on this line. So for this simple equation, the characteristic curve is linear. We have an infinite number of characteristic curves, which can be parameterized by the constant c. And on each curve, the value is constant. And this allows us to reach the following formula. The value of our solution in the current point x at the next time step equals the value of function in a step near the point in question at the current time step t. Usually this can be shown on a picture like this. So these type of pictures are very common when we talk about one-dimensional equations in partial derivatives. We have one axis corresponding to the spatial coordinate x, where we mark the points of the grid. X with subscript m is the current point, and we have the nearby points given by indices m-1 and m+1. The other axis is the time axis. So basically, since the function of the solution depends on two variables, x and t, it is defined in this whole region. Or more precisely, it's defined in a square with borders x from 0 to 10 and t from 0 to the t capitalized. However, since we are using numerical methods, we know the function values only in a discrete number of points. So here at the known time step marked by the superscript n, the function values are represented in these gray circles, meaning that we already know these values. And our goal is to find the values at the next time step, at the n plus first time step, which equals t plus dt. And we don't know these values, therefore they're depicted by empty circles, and the actual value in question on the next time step can be found using the characteristic property. So this line, straight line between these 2 points, is the characteristic line, the characteristic curve. And we know that the function value here equals to the function value here. So we simplify our problem from finding somehow the unknown value at the next time step to finding the value at the known time step, which can be done by interpolation. Basically, I'm just repeating what you already know about the grid characteristic method. Also, as you know, one of the very important properties of finite difference schemes is stability. And in order for this scheme to be stable, the current stability condition has to be satisfied. And this condition is given by the following relations, meaning that the time step tau, or dt, whatever you prefer to call it, is less than the grid step h, which is the difference between 2 points on the grid, divided by lambda, where lambda is velocity. The question now is how to improve the accuracy of this scheme. The simplest way is to interpolate this value in this triangle position using linear interpolation. However, its accuracy is not very good, which can be seen in numerical calculations. So we are trying to improve the accuracy by interpolating this value with a higher order polynomial. One approach that you have already discussed is using wide stencil. For example, when you are using 2 points, you can only construct a linear interpolator, and it will result in the first order of approximation. But if you use these 3 points, you can construct a second order polynomial, and the order of approximation will be 2. However, such wide stencil using multiple grid points has its disadvantages, and in this lecture we discuss another approach based on the differential continuation of equation 1. Basically, we take the original equation, here it is, and we differentiate it with respect to spatial coordinate x, assuming that the solution is smooth. Then we obtain this equation. We can change the order of the differentiation in the first part, obtaining this form of the equation. Then we can introduce a new function v equals the derivative of u with respect to the spatial coordinate x, and obtain this equation. So this means that we have another equation of the same form as equation 1, but with respect to a different unknown function v. And the important thing is that v is related to the original unknown u, being its derivative with respect to x. Also, the original values of v can be found by differentiating the initial condition of the Cauchy problem. There's a question with boundary conditions for v. However, if we consider this problem, we can also use the same boundary condition for the function v. And now we are going to solve both problems, both Cauchy problems for u and for v functions simultaneously. We will be using grid characteristic method, so we will have to find values of u and v at the point x minus lambda dt, and the trick is to do this procedure simultaneously, raising the order of approximation. The idea of this joint interpolation is as follows. Let's take a look at this picture. We have the spatial axis x, and on the y-axis we depict the function values u. We consider 2 points of our computational grid with subscripts m and m-1. So in these gray points, we actually know the function values. The function itself, the true solution to our equation, is represented by a solid black line, and this is how it's going. We can see that the function changes significantly in the region between these 2 grid points, and the linear interpolation results in a value very far from the exact value of the function, which means that the error of the numerical solution will be very high, and in order to increase it, we will have to diminish the grid step and add some extra points here. However, if we know the derivatives at this point and this point, these derivatives, and we know them because they are values of the function v, because we know that function v is the derivative of the u function. And these derivatives, they set the direction of our function in these points, which allows us to construct a third-order polynomial. Here it's depicted by dashed line, and the interpolated value by the procedure of this interpolation with the compact scheme results in a much more accurate value. Thus, the accuracy is significantly improved, and the interpolation order is raised to 3. There's a question about how we are going to construct this third-order polynomial. I am not going to present the whole procedure, just hint how it can be done. Basically, if we want to interpolate or approximate a function within this line segment with a third-order polynomial, we can write it like this, with the set of 4 unknown coefficients, which are just some parameters that determine the polynomial. Knowing this, we can actually calculate the derivative, also depending on the parameters a with subscript I, and then knowing 4 values of the polynomial itself and its derivative, we can obtain a system of 4 equations. So basically, we substitute the argument into this formula. We know the values in these points because the values of the polynomial are the function values u at the grid points, and its derivative are function values v at the points of the mesh. So we have totally 4 equations and 4 unknowns, and the system can be solved analytically, thus finding the approximating polynomial. And then when we have the polynomial defined by these coefficients, we can calculate its value at any point inside this subdomain, just substituting this point into this formula. So I hope this is clear, and now we can discuss the implementation, which may provide some further explanation and intuition into it. So we start with simply importing several libraries. The next function sets the initial conditions because we are solving the Cauchy problem. So we need to know the initial values of our unknown functions. And here they are set in a separate function. Basically, we initialize our mesh and the coordinate values at our mesh. Then we select a small line segment and generate the impulse in the form of sinus in the power of 4. And the derivative is the derivative of this function. So we have 4, we have the power of 3, sinus and cosinus. And in this cell, we actually plot the initial condition. So we can see that the total computational domain is from 0 to 10, and in the subdomain from x equals 1 to x equals 3, we have a smooth initial function. It is very important that this function should be smooth if we want to check the accuracy and convergence order of our scheme, because on discontinuous solution, the order will probably be we will probably obtain the first order scheme. So this function allows us to set the initial condition of any form that we like. And here we have a smooth function, the fourth power of sinus. Now we discussed the interpolation procedure. We expect that lambda is positive real value, real number. The polynomial is of the following form. So basically, it has the x is the independent argument, and a, b, c, and d are the coefficients which have to be found. We also have 4 values of the function, and we have these parameters which define the point in which we will interpolate our polynomial. And this function returns u and v. It returns 2 real numbers interpolated in the point inside. So this function takes values in these points, here and here, and returns this interpolated value. We can see the implementation of the function. The system of algebraic equations is solved analytically, and the following coefficients are found. Then we define x as the point for interpolation, and then we calculate the values on the next time step, just substituting the x into the polynomial formula. both for u and for derivative v. It also should be noted that here we consider that the current point has the coordinate 0. The thing is that the actual coordinates are not important for the function interpolation. We only need to know the distance between the points, which is given here as an argument of function. So this is just an auxiliary function which reconstructs the value at the next time step by interpolation. And here it's implemented only for the case of positive lambdas. And it just calls the interpolate function with the values of the function itself and the values of its derivative in the current point and in the point to the left. One of your tasks will be to implement this for the case of negative lambdas. So when this value is less than 0, then you will have to use the interpolation procedure, but use the values to the right, which are given here. Okay, so next we have the function which just an auxiliary function that saves the values at the current iteration in the history array. Normally you would save data to the disk and try to do it efficiently, but here we have a small one-dimensional problem, so we can just store everything in memory and not use the hard drive. And now this function, run simulation, is actually the main function of the whole code, which determines the numerical method. So we get the number of points in the mesh as a parameter. Knowing number of points, we can calculate the size of the grid step. Then we can initialize with zeros our function at the current time step, both function and derivative, and on the next time step. Then we call the setInitial function, which initializes the u and its derivative to the sinus impulse. Then we have a loop over time steps, and each time step we perform saving. Every save step iterations in the internal points of the region, we reconstruct the values on the next time step using the reconstruct function. So we give to this function values of the u in the point in question, g, and the neighboring points, -1 and +1. We do the same for the derivative. And we also pass parameters lambda multiplied by the time step and the grid step. So this procedure is performed on every time step, and it finds the values on the next time step in every internal point of the mesh. I'm stressing the fact that you need to handle the boundary values separately. Basically, you just don't have the neighboring points either to the left on the left side of the region, or you don't have the point to the right when you are at the right side of the region. So you need to handle the boundary in some specific way. Here, on the left boundary, we have 0 boundary conditions, which is automatically satisfied because the functions are initialized with zeros, so we don't have to check it. However, we do have to run the calculations on the right side of the boundary. We get the last element of the array by the -1 argument to the array, and we run the same reconstruct procedure, and as the next grid points we just pass none values because there is no point next to the right from the right boundary. And afterwards we swap values of our array on the current time step and on the next time step, which effectively finishes our step of our computation. And all this procedure is repeated in the loop number of steps times. Here we have an example. We define time step so that it would satisfy the current stability condition. We defined parameter lambda and parameters of the computations, define the array for saving values, and perform the simulation. And here we are just plotting the computed values. So this picture depicts the value at the starting point in time, our impulse. Then we see that this impulse is propagating to the right, and in the final point of the computation it reaches this position. And if we look carefully, we can notice the degradation and the errors introduced by the numerical solution. Essentially, in the beginning, the amplitude of the signal was equal to 1. And in the end, we have the amplitude around 0.9, maybe 0.95. So we have a degradation in the accuracy of the solution. And we also may notice the negative values, which we will discuss in some details later. So now we can actually investigate the approximation order of the presented scheme, because, as you know, there are many different schemes. You already discussed some schemes on the previous lessons with Vasily Golubev. So there's a question of comparing this scheme to the rest. When we want to investigate the order of approximation or convergence in this case, basically we study how decreasing grid step sizes influence the solution. We expect that when the steps grid step h and time step dt are smaller, we expect that the arrow will also be smaller. But the question is, how smaller will it actually become? The error will be computed as the norm between the difference of the analytical solution with this hat and the numerical solution on the grid, and the norms used. These are just norms in the discrete spaces. So the L1 norm, which is a sum of absolute values actually multiplied by h. Okay. Maybe later we'll fix it. And the approximation order is this formula gives the approximation order. It's the definition of what an approximation order is, and P here is actually the approximation order. And if we compare the arrows with grid step H and with the grid step twice larger, then we will have we can calculate the numerical convergence order P as the logarithm of the of this fraction of errors. It should be noted that decreasing grid step requires the appropriate decrease in the time step because the courant stability condition has to be satisfied. So here is our stability condition. When h is taken twice smaller, we actually have to take tau also twice smaller. So taking the tau smaller results in the fact that we need to perform more time steps, obviously, and the smaller grid step means that we have more points to take into account, and we perform calculations in more points. Therefore, in a one-dimensional problem, when we decrease the grid step h by the factor of 2, then each next computation will take 4 times longer than the previous one. So the idea for investigating the numerical order of convergence is as follows. We fix a certain problem for which we know the analytical solution. Then we run a series of computations with the same scheme, but decreasing grid steps and time steps. Then we take a look at how the errors are changing and calculate the approximate numerical order of convergence. And the higher this value is, that means that the errors decrease quickly with the diminishing time steps, and it results in the fact that running the same running simulation with the same number of points in the mesh and the same number of time steps, but with different schemes and of different order, we can significantly improve the quality of the numerical solution. So here we can actually initialize our 4 tests that we will run. The number of points for the first test is 101, and for each next test we will have twice as many grid points. The time step will each time be smaller by the factor of 2. Number of steps will also increase each time by the factor of 2. And then we will save the computed errors to these arrays. So here in this cycle we run all our tests. So we call run simulation multiple times. That's why we separated the functionality in a separate function. Then we calculate the exact analytical solution, which is the same impulse that was set in the initial condition, just on a different line segment to the right from the initial segment. And finally, we can calculate errors. First, we take the absolute difference between the exact solution and the analytical solution, which is stored in the history array. I means the current test, and -1 means that the last saved values will be taken, meaning the last time step. And then we actually compute the errors, either as the maximum difference or the sum of this diff array multiplied by the grid step of the current computation. And finally, we can print the resulting values. We see that each time we reduce the grid step, and the errors reduce also significantly, which is seen here. At first, we have just 0.09 approximately, which is almost 0.1, and at the final step we have 0.0003 approximately. And the similar situation is with the other norm. And when we calculate order, which is P, which is calculated according to this formula, we can see that the order is greater than 2 from the beginning, and it gets closer and closer to 3. This means that 3 is the theoretical convergence order of the scheme, and we have implemented the scheme correctly so that the numerical solution also converges to the analytical solution with the order almost 3. If we continue these tests further, we can actually see that the p values will get even closer to 3, like 2.999. So we have discussed the concepts of approximation order and convergence order, and in this lecture I have presented the way to improve the order of the numerical scheme by using the differential continuation of the equations. One of the main advantages of this is that the interpolation procedure is performed only in one line segment between just two neighboring points, so no extra points are required. The stability condition for this scheme remains the same as for the schemes you discussed on previous lectures. And another important concept in numerical methods that we will discuss today is monotonicity. In this picture, you can see again the result of the comparison between the analytical solution in orange color and the numerical solution in blue color. The obvious difference is here that the amplitude of the numerical solution is smaller, but another important difference is that the analytical solution was positive in the whole region, and it was never negative at any point of the computational domain. But the numerical solution, actually due to numerical errors, actually got below zero on this graph. So we have negative values. And in some applications, this is very troublesome and problematic because some functions represent certain physical quantities which can never be negative, and obtaining the negative value in a computation, even if this value is rather small compared to the amplitude of the solution, still it is a problem. Another problem is the solutions with extremely high gradients, in which non-monotonous schemes create non-physical oscillations, which can sometimes make the analysis of the computation much more difficult. So numerically, this is described by the concept of monotonicity. One of the definitions is the following. Consider that we have function u at points i-1 and I. We want to interpolate this function at this point, which is between those two, which is presented here. And basically, if the interpolated function is the interpolated value is between the minimum and maximum of the values on the boundaries, then this scheme is called monotonous. If this property is not present, if it doesn't hold for certain situations, then the scheme is non-monotonous. It is obvious that first-order schemes are monotonous, but it has also been proven that any linear monotonous scheme cannot have the order of approximation higher than 1. So basically, we have a certain problem that we want to raise the order of approximation and the order of convergence in order to decrease the overall computational error. But when we do that, when we utilize higher order schemes, we encounter the problem of non-monotonous solutions and non-physical oscillations, which are difficult to interpret. So there are several ways to counteract this problem. And one of the ways is using higher order schemes, because we need higher order schemes. We need to improve the accuracy of the solution, but we can introduce some special maybe correction procedures which would improve the monotonicity property of the scheme in question. One of such ideas for that is the use of special limiters or monotonizers. Here you can find, in this link, the description of quite a lot of these limiters, but basically it's the simplest one. MinMax works as follows. So it gets the function value on the left, the function value on the right, and the interpolated value, which we have already interpolated by a certain procedure, maybe of first order, maybe of third order, it doesn't matter. Then we compute the minimum of these two values and the maximum of these two values. And then we say that if our interpolated value in the middle is less than minimum, then we simply return the minimal value. If it's greater than maximum, then we return the maximal value. And if it's between the minimum and maximum, then we actually return the interpolated value u. So here we have the run simulation limited function, which is almost the same as the original function run simulation, with this minor difference. So on each time step here, for each point in the internal part of the region, after we reconstruct the values, we perform this correction procedure. So here in these lines, we fill the values on the next time step by a straightforward interpolation by the compact scheme of the third order. And here we make sure that if at some points the interpolated values are less than minimum or greater than maximum, then this function will correct them here and return the limited values. And here in this cell, we have run the tests for the limited, for the simulation with these special monotonizers, and it results in the following order values, the following errors. And what we can see immediately is firstly that the order is much smaller. When we use the scheme without any monotonizers, we had the order almost 3, and the error was decreasing very rapidly, which can be seen here. And now with this monotonizers, the order is smaller and the overall error is greater. However, if we compare the plots, we can see that the numerical solution without monotonizers is much better in terms of the amplitude, but it has negative values, which are probably non-physical, because the physical quantity in question should not have any negative values. It can only be positive. And the numerical solution with the MinMax limiter results in this blue line. So yes, we lose a lot in terms of accuracy and in terms of convergence order, but no negative values are reconstructed, and the values of the blue line can be considered more physical. So that's all the new information that I wanted to tell you about today. The tasks for you are the following. Firstly, I suggest that you add, for example, the first order interpolation procedure. You probably have already seen it in code from previous lessons by Vasily Golubev. So basically, the interpolation procedure is defined by this function. You can either replace it or add your own function like interpolate 1 for the first order interpolation, and then call the accurate function here and run the computations and see the difference between the numerical methods of different order. Another task is adding a non-smooth initial. So basically, you can add a rectangular impulse, meaning that in the set initial function, you will just have to replace these lines by setting constant value, for example, 1, and then study the performance of different interpolation schemes and the use of monotonizers. And you will see that the error values in general will be greater for the rectangular impulse, and the approximation order will be lower. But high order schemes without monotonizers will create non-physical oscillations near the discontinuities of the solution. And another possible task is to modify this code to work with the negative velocity. Basically, you will have to interpolate using values in the current point and in the point to the right. So that is all for today. Are there any questions?
Students, do you want to ask some questions? Or you can mail to us. Alex, do we need to inform them regarding their exam or test?
Actually, I think that maybe Vasily Golubev will inform them better, or maybe he will email them or someone. I'm not just very familiar how it will go with the procedure next time on the exam.
Oh, okay, no problem. Thank you very much for the very informative lecture. And I think students will mail us their queries.
Okay, thank you for your attention. Goodbye.
Goodbye. Thank you very much.